This is Chapter 12, Section 1, Sequences and Series. First of all, let's start out with what a sequence is. A sequence is a function that computes an ordered list. For example, and I'm going to use familiar notation with you to begin with, if f of n is 100n, it's a function of n. By the way, n is, generally speaking, the independent variable used with sequences instead of x. That's one way that we'll know that we're dealing with a sequence. And what it gives us as an output are just the outputs separated by commas. So unlike a lot of other functions we've dealt with, where we might list ordered pairs, what we'll do is we'll substitute in, say, 1 times 100 is 100. Then substitute in 2, 200, comma. Now substitute in 3, 300, etc. And so a sequence is a list of outcomes that you get when you substitute in the numbers 1, 2, 3, 4, etc. And so that means that the domain for sequences is the set of positive integers. So we're only using positive integers as inputs. And so there is no such thing as, well, what is f of 1.2, or what's f of pi, or f of square root of 7. Those are not valid inputs. The only things we can put in are the numbers 1, 2, 3, 4, etc. Okay? So a finite sequence is a function that has a set of natural numbers of the form 1, 2, 3, etc. up to n as its domain. So what I've set up here is an infinite sequence, where we're going to use all of the positive integers, giving us an infinite sequence. A finite sequence, on the other hand, stops. So that domain would be, I'll put in 1 and 2 and 3 until you get to n and stop. That will give us a finite sequence. It doesn't go on forever. It stops as soon as you put n into the formula. All right. So this notation I've been using, f of n, is actually not used. In functions, we like to call them functions, normal functions, like we've dealt with for years in all of your algebra and this course until now, except for trig where we use theta. But anyway, we still used function names like f and g and h. Instead, we're going to use lowercase letters like a and b and c. And the notation that we might see is a sub n or b sub n or c sub n. And so instead of writing f of n equals 100n, we might say that a sub n is the name of this sequence, and the formula for building that sequence is 100 times n. And so when I put in 1, I'll call that the first term. When I put 1 in for n, of course the arithmetic here isn't hard, and then the second term is denoted by a subscript 2. So the first one was a sub 1. This is a sub 2, meaning the second term. And that means substitute 2 in. So instead of using, up here we would have said f of 1 is 100. Instead of using that notation, we're saying a sub 1 is 100. So that's just a little bit different. And so what we end up getting is a sub 1, comma, a sub 2, comma, a sub 3 in a generic sense, a sub 4, comma, dot, 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 for an infinite sequence. And if we wanted to stop, we could stop it by saying comma a sub n, and then we're done. Now those three dots mean keep on going in the same pattern. So that's a way to say keep on going, like this sequence up here, 100, 200, 300. Keep on going in that same pattern. Okay? Or this a sub 1, a sub 2, a sub 3, a sub 4, comma, dot, dot, dot means keep going until you get to a sub n, and then you stop. All right. So that's kind of the notation that sequences have and what we'll use. And let's work on a few examples. So example A. This one is named A. The sequence is a sub n. And we can get the terms of the sequence using this formula, n plus 1 over n plus 2. By the way, what we're seeing here are what we call explicit definitions. So these are explicitly defined sequences. This is where your a sub n is some function of n, like the one we're currently working on, where a sub n is n plus 1 over n plus 2. That's a function of n. It's an expression that has n in it. Okay, so anyway, a sub 1 would be 1 plus 1 over 1 plus 2, which is 2/3. Oh, and the directions were find the first 5 terms. So that's what we're doing. Then we put in 2. That'll be 2 plus 1 over 2 plus 2, which is 3/4. A sub 3. Now we're substituting in 3. 3 plus 1 divided by 3 plus 2 is 4/5. A sub 4. 4 plus 1 over 4 plus 2 equal to 5/6. And after you've done a few of these, you might actually, instead of technically doing that substitution, which I guess you could always do, instead what you might find yourself doing is saying, well, I know what the next one's going to be. I can follow the pattern. The numerators start at 2 and go up by 1, 2, 3, 4, 5. So the next one should be 6. And the denominators also tend to go up. They start at 3, 3, 4, 5, 6. So this one should be 7. And if you did the substitution, that of course is what you would get. So at any rate, this sequence, which we got by substitution into our formula, until we'd seen enough of them, like 4 or 5 of them, and say, hey, wait a minute, I think I get the pattern. I think I can extend this without substitution. And that's good. That's one thing I want you to be able to do. That's a good skill to develop. Because once you can detect patterns, you're going to be in a good shape for being able to do all kinds of problems. Now, this textbook tends to like a sub n. It could have been b sub n or c sub n, but I'm going to stick with what they have written. But don't think that it has to be a sub n. It can be any of those first 3 letters are the typical ones that you see the most anyway. Okay, so a sub 1 is negative 1 to the first times 1, which is negative 1. A sub 2 is negative 1 squared times 2, which is positive 2. A sub 3 is negative 1 cubed times 3, which is negative 3. A sub 4 is negative 1 to the 4th times 4, which is 4. A sub 5. Well, let's see. Do you see a pattern? Well, it looks like because the powers on negative 1 are going up, the sign of the answer is going to alternate between negative and positive numbers, because we know negative 1 raised to an odd number gives us negative 1, whereas negative 1 to an even power gives us a positive 1. So it looks like this one the next one would be negative, because the last one was positive, And the numerical part of this without the sign is just going up by 1 each time. And of course, if I got that by substitution instead, there's nothing wrong with that. I'm just saying if you can see a pattern, it's a good idea to test your ability to see patterns and try a few. And if the pattern doesn't work, see if you can figure out why you weren't able to see the pattern. If the substitution doesn't give you that same answer your intuition did about the pattern, then go and check out and see what's going on and what you missed. Okay, C. This is a sub n is equal to -1 to the nth divided by n. Okay, so a sub 1 is -1 to the first divided by 1, which is -1. A sub 2 is -1 squared divided by 2, which is 1/2. A sub 3 is -1 cubed divided by 3. And since we just did the other one, you may notice this one faster has alternating signs. So this one should be positive, and it's always 1 over the next bigger number. So that should be 1/4. You can try substitution and double check that. And the next one should be negative and 1/5, -1/5. So see if substitution gives you those answers correctly. Gives you the same thing as what I think the pattern is, and it does. So those are the first 5 terms of that sequence. Okay. All right. Now, a little bit of vocabulary here. We have something called a convergent sequence, and then there's something called a divergent sequence. A convergent sequence is one whose terms get closer and closer to some real number, like this last one, even though the signs are alternating. Do you see that those are getting to be bigger and bigger denominators, with the numerator always 1, and 1 divided by 10, if you think about its value, 1 divided by 100, 1 divided by 1,000,000, those are getting closer and closer to 0. So I would say, at least from just our idea of how things are working, I would say that this one probably converges to 0. Okay, converges to 0. One way to see that is to graph the sequence. This will be the n-axis. This will be the a sub n axis. Since the only n's we can use are 1, 2, 3, 4, 5, etc., I'm going to put those numbers down here. You don't have to number every one of these. Just putting a 1 on the first mark is sufficient, but I'm doing it this time for clarity. Okay. Oh, I didn't give myself enough room here. Let me move this up so I can get a little bit further down. And there we go. So let's say that this is 1 away. So this would be -1. And when n is 1, we got -1. So we graph the point 1, -1. 2, we got 1/2. Now, of course, I'm guessing about where that is, and it's good enough. 3, -1/3, +1/4, -1/5, 1/6. And you can see, although they're oscillating between positive and negative values, they're moving in toward n equals 0. And if this were a function, what would we call this line that it's approaching? Right, it would be called a horizontal asymptote at y equals 0. So one of the things about convergent series is that if you were to graph them, they converge on a horizontal asymptote, if they actually converge. Not all sequences converge, but this one does. Oh, and by the way, did you notice I did not connect the dots? That's because there's only inputs that are numbers like 1, 2, 3, 4, 5, 6. not anything in between. So we cannot connect the dots. It's not valid to try to do that. It's not a connected, in fact, it's just what we call a discrete set of numbers. They're just discrete dots. They're not connected. So anytime you graph a sequence, it will not be connected. Okay, so let's look at this one. Let's graph this one just for fun. You say fun? Wow, Mr. Ford. Wow, you are out of touch, dude. Well, I think it's fun. So this is going to be the set of numbers for n. And I'm going to take a good look at the answers I have and make my one on this axis sort of agree with the type of answers I see I'm going to get. And so when n is 1, we get -1. So unfortunately it's right there where I wrote 1. Oh well. 2 was 2. And 3 was -3. Then 4. Then -5. 6, which is above what I gave myself. And you can see that this one is not headed toward a real number. They're oscillating, and these are getting further and further away from 0. So they're not converging toward 0. So what we'll say here is that this one diverges. If it doesn't converge, then we'll say it diverges. Okay, let's look at the first one of these three that we did. Think about the numbers and tell me without a graph, at least at first, what do you think is going on here? Does it converge? And if it does converge, to what do you think it converges? So while I'm setting this up, you give that some thought. Okay, so let's graph this guy. 1 is 2/3, which is about right there. Then 3/4, then 4/5, then 5/6, 6/7, 7/8. Do you see that those are increasing each time? Is there something it's headed toward? Like later on, don't you think there'll be like 99 over 100? 9,999 over 10,000. 1,000,000 over 1,000,001. What are those getting closer and closer to? Because I think they do converge. Would you agree? I think they converge to 1. There's this horizontal asymptote at y equals 1 for this graph. And so our conclusion would be, yeah, I think this converges, and I believe it converges to 1. Okay. All right, so that's just a few examples to kind of get our feet wet and kind of work with the new terminology, convergent and divergent. All right, so let's look at another example. If a sub n were n squared, that would be 1 squared, 2 squared, 3 squared. Oops, started to write 3. I was actually trying to write the results without slowing myself down as much as I did in the first few examples. So 4 squared, 5 squared. And I really do think you can skip writing what I did up above to a certain extent. That's fine. Okay, so what do you think? Converge or diverge? Well, these just increase without bound. If you know perfect squares, they're just going to get bigger and bigger and bigger. So they do not approach any particular number, and so this sequence diverges. Anytime the sequence increases without bound or decreases without bound, it will have to diverge. Okay. The line converges if all of the terms are approaching some value. Now, these have all been, as I said, explicitly defined sequences. Now we're going to talk about something called recursively defined sequences. And before I leave the explicitly defined ones, I do want to say that the strength of a formula that's explicit is that if I wanted to find, like, okay, what's a sub 10? Well, all I have to do is put that into the formula and calculate the answer. Could I find a sub 53 if I wanted to? Sure, I could. But I don't need to find anything else besides that one. If I have this formula, a sub n equals n squared, I can find any term someone asks me to find. So I could find the 53rd term by saying a sub 53 equals 53 squared, which is, well, whatever it is. I think it's about 2,809. Yeah, that's right. Anyway, the difference between that and a recursively defined sequence is that in a recursively defined sequence, you're defining the next term in terms of what you already know. So in terms of prior answers, prior terms. So here's a recursively defined sequence. This is our first example of this. I'm going to tell you that a sub n is found by taking the answer right before it, which we're going to call a sub n minus 1 is the answer right before a sub n. Like if a sub n were 7, the term before it would be a sub 7 minus 1, a sub 6. So a sub 6 would be the term right before a sub n. We're going to take the last term we knew, we're going to double it, and then add 1. So you may be thinking, well, yeah, but don't I have to know where to start? Yes, that's important. So the recursively defined sequence actually consists of two parts. You have to give me at least one of your first terms so you can get started, and then what formula produces other answers. So a sub 2 is going to be 2 times the last answer, which was 4, plus 1. So that a sub n minus 1 in this case is a sub 1. It's the one right before a sub 2, and we get 9. A sub 3 is going to be 2 times the last answer, a sub 2, and that answer is 9, plus 1 is 19. Okay, a sub 4 is going to be 2 times the last answer, plus 1, which is 39. I think that's all it asks us to find were the first 4. So 4, 9, 19, 39 are the first 4 terms. And of course, we could indicate that it could continue by putting ... after that. The weakness here is that if I all of a sudden said, okay, that's great, I've got the definition, got it going, it's all in my head, what's a sub 10? Well, to know what a sub 10 is, I'll have to know what a sub 9 is, right? Double it and add 1 to get a sub 10. Well, to know a sub 9, I'd have to first know a sub 8. And to know a sub 8, I'd have to first know a sub 7. In other words, I'd have to go all the way back to the beginning of the sequence and build it up to the 10th term. I couldn't just simply substitute 10 in and directly get the answer. An explicit definition for that reason is way better. I can put 10 into this formula up here and immediately get the answer of 100. But down here, I have to build the sequence at that point. That's the biggest negative about recursively defined sequences, is that you can't just skip and say, well, what's the 53rd term? What's a sub 53? I don't know. I have to know the first 52 before I can answer that question. Or at least I have to know what the 52nd term is, I should say. So that's the weakness of recursively defined sequences. But the strength is that it's how most of us think. So in a little while, we're going to be given sequences and asked to find a formula for it. Most of you will think automatically of a recursion idea. What do you do to the last answer to get the next one? That's the way your mind is going to work through this, more than likely. And so you're going to easily come up with a recursion formula and not the explicit one. Although the explicit one's better, it's more powerful. Your mind is going to go to the recursion idea naturally. So the intuitive nature of recursion, we are going to give a nod to that so that we understand how it plays a role. But we're not going to use those nearly as much as the explicitly defined ones. Anyway, if the first term is 2 and the next term is the prior term, a sub n minus 1 is the prior term, plus n minus 1, this one uses n as well, and that's okay in a recursion formula to use n. The last one didn't, but notice it does. The hallmark of this is that it uses a prior term, and so that's how you'll have to do this. So a sub 2, that's going to be a sub 1, which is the last answer, plus n, which is 2 in this one, minus 1, that's 3. Okay, a sub 3. That's equal to a sub n minus 1, so that'll be a sub 2, so that's the last answer is 3, plus n, which is 3, minus 1 is 5. Okay, a sub 4 is the last answer, so 5, plus n, which is 4, minus 1 is 8. I think that's all we have to find in the first 4 terms. So this is 2, 3, 5, 8. All right. So now going on to modeling insect population growth. We're told that the winter moth population in thousands per acre in year n is modeled by this recursive formula. A sub 1 is 1. A sub n is 2.85 times the prior term, a sub n minus 1, minus 0.19 times the prior term squared. And so we're supposed to give a table of values for n equals 1 to 10, and then graph the sequence and talk about what's going on with these moths. So let me see. So for part A, we're supposed to give table of values. So if n is 1 through 10, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Excuse me. So a sub n is going to be for 1, a sub 1 is first term is 1. That's good. Then for a sub 2, our a sub 1, our prior term is 1, so that's going to be 2.85 times 1 minus 0.19 times 1 squared, which is 2.66. Okay, then a sub 3 is going to be 2.85 times our last answer. So take the last answer, 2.66, put it in for a sub n minus 1. So 2.85 times 2.66 minus 0.19 times 2.66 squared is about 6.236636. I'm going to round it to fewer places because we're going to graph it, so it's not as crucial. So I'm going to round that to 6.24. Okay, and I'm going to keep going. For a sub 4, it's going to be 2.85 times that 6 number. I'm not going to say the whole thing. That 6 number minus 0.19 times that 6 number squared. And that gives us a number that's about 10.4. I'm doing a lot of rounding. And by the way, I'm keeping that number in its entirety when I do my calculations. I'm not actually typing in 6.24. I'm using that 6.236636 number that was in my calculator times 2.85 minus 0.1 times that same number squared. So I'm using that storing and recalling feature of our calculators that we've learned to use. Okay, so for 5, 2.85 times our last answer, 10.4, minus 0.19 times 10.4 squared. And when I say 10.4, please remember that's a rounded version of what I'm actually typing in my calculator. And I get 9.11. So an n is 6. I take that answer times 2.85 minus 0.19 times that same 9.11 answer squared, and I get 10.2. And for 7, I get 9.31. For 8, I get about 10.1. For 9, I'm getting 9.43. And for 10, I'm getting 9.98. Okay. Then for part B, we're supposed to graph that. So Rn was the year number. So I'm going to label that. Since it's a word problem, we should probably relate it to the words of the problem. And on our A sub n axis, that's the insect density is what we're calculating, the insect density. And that's in thousands per acre. Okay, so like in year 3, it's 6.24 thousand, so about 6,240 insects per acre. All right, so looking at our numbers, looks like a lot of them around 9 and 10, so I think I'm going to make this 2, 4, 6, 8, 10. And of course, this would be year 1, year 2, 3, 4, 5, 6, 7, 8, 9, 10. Alrighty. So we're ready to graph. So 1 is 1, 2 is 2.66. Now remember, this is 4. The second mark is 4. I'll write that in this time. That's about 4. So 2.26 is about right here. Okay. 3, we should get 6.24. 6.24 is about right there. And then for 4, we should get 10.4, which is about right there. And then 9.11, so 2, 4, 6, 8, 9 is right there. Go up a little bit for 0.11. It's about right there. Excuse me. And then 10.2. It's about right there. 9.11. Oh, I already did that one. 9.31. It's about right there. 10.1. 9.43. 9.98. And you might see, let me try to draw something in without obliterating everything, that it looks like there is a line somewhere that they're approaching, and it looks like they're going above, below that line. So it kind of oscillates above and below the line, but every next one is getting closer and closer to that line. And as it turns out, if we did this for a long time and gathered a whole lot more data, in other words, expand your table, you would find out that this stabilizes near about 9.7 thousand per acre is what the density heads towards. Okay, so you write that as a sentence. The population stabilizes. In other words, gets closer and closer to the value of 9.7 thousand per acre, thousands per acre, for the insect population. All right. So now the next thing I want to talk about is if we were to add the terms of a sequence. Let's say we have a sub 1 plus a sub 2. Instead of commas, we're separating these by plus signs. This is what we call a series. A series is the sum of the terms of a sequence. So you just take the sequence, and instead of putting commas between, you put plus signs in between, and that gets you a series. And what I've written here is the idea is that this is an infinite series. And of course, if I went, say, this far and then stopped, this would be a finite series. And if I say series, generally, unless the word finite is in front of that word, if I say series, I'm generally talking about an infinite series. So although technically we could call this an infinite series, we're just going to embrace the term series and imply that it's infinite whenever we're dealing with it. And if we want it to be a finite series, we will put the word finite in front so that you know that you're dealing with just a certain number of terms and you stop. Now, the Greek letter sigma is a good symbol for saying mathematically that we want to find the sum of things. This is the Greek letter sigma. It's capital sigma, and it's used to indicate a sum. So when we see this sigma, what it's going to involve is an index of, let's say, a variable like I is pretty common for this. Other letters that you may see are like I and J and K and N. Those are index variables that are used. And in this particular one, I'm going to start with 1. You don't have to start with I equals 1, but for right now, that's probably safe because it makes counting them easier. You'll see why I say that in just a second. And that goes below the sigma, and where we're going to stop goes above. So this is the upper limit of the sigma. Let's say it's 5, just for example. And then behind that comes a formula for producing the terms of the series. And so that's going to be your A sub n formula. This will be, because the variable's I, it'll be A sub I. So that's kind of generic. In fact, let me make it even more generic. To start with, let me make this not be 5, but it could stop at a more generic n. So I'll change that. I'll make a specific example here in a second. So let's say that's n generically. And of course, what that means is we're going to start with 1 and put 1 into that formula for I. So that'll give us a sub 1. Then plus, because it's sigma, that means add. Then we're going to put 2 into that formula, which gives us a sub 2. Plus, now put 3 into the formula, a sub 3. Plus, keep doing that until you finally put in n. And once you've put n into your formula for I, that's your last one, and you're done. And so this is what we call a partial sum. Like this one up here. Come up here for a second. Look at this one again, this finite series. Since that's the sum of the first 4 terms, that's denoted by capital S for sum of the first 4 terms. So let me give you another expression. S sub n is what we call the nth partial sum of a series. The nth partial sum. So S sub 4 is the 4th partial sum. S sub 10 would be the 10th partial sum, etc. And so I told you we'd do an example that's a little bit more concrete. So let's start with I equals 1 and go to 5. And let's make our formula, let's make it I. Simple I. It's pretty simple. So put 1 in for that and you get 1 plus. Now put 2 in for I plus. Now put 3 in for I plus. Now put 4 in for I plus. Now put 5 in for I. And that's S sub 5. The 5th partial sum. And of course, since you now have numbers, you can add those. I believe that sums to 15. And get a 5th partial sum. Now, one thing I'm going to say that I don't agree with the way the book does this, but I'm going to show you what they say. In calculus, if you have an infinite series that converges, it's going to converge to the sum of the series S. S is the sum of the series, if it converges. So I'm going to write sum of the convergent series to be a little bit more accurate. And the notation they use in this book instead of S is S sub infinity. So it's like S sub 5, but instead of adding the first 5 terms, you're adding infinitely many terms. And I suppose that's okay. I don't really like it that much, but this book uses it, so I guess I'll give a nod to it, at least say, oh, well, that's a thing. I guess it exists. And so this infinite series in sigma notation would be, you're starting with I equals 1, and our formula is going to be some A sub I formula, generically speaking. And this time we're going to go to infinity. Now, you having infinity on top of sigma is a calculus thing. It's just that S sub infinity isn't used in calculus, it's S. But that's pretty close, so it's not too bad. So we'll let it go at that for now. So I want to do another example, but I'm out of room on this slide. So what I'm going to do is I'm going to close this and open up the next one. So I'll see you for the next part of this set of recordings.